video, we're going to start taking a look at electrolytic cells. So in an electrolytic cell, it's a little different from a voltaic cell in that you're using a non-spontaneous chemical reaction and forcing it to happen. So you're taking electrical energy, either in the form of a battery or hooking it up to, an electrical plug, electrical socket, but you're taking electrical energy and converting that into chemical energy. So you need a flow of electrons to start with. The noun electrolysis is when a current is forced through the cell. It forces the chemical change to happen. And this is a cell where normally, the E of the cell is negative. So normally this wouldn't happen by itself. This is not going to produce a flow of electrons by itself. You need a flow of electrons to get this started. You need a power source. You need some sort of battery, some source of electricity. The delta G is a positive number for this. So this is a non-favorable reaction. It is not spontaneous. And you need this external power source to couple along with this reaction to make it happen. So your external power source needs to have a potential that's greater than the absolute value of your cell potential. So if your cell potential is like -3, you need to have -3 volts. You need a battery that is 3 volts or greater in order to make this reaction happen. And some things that this is used for is like recharging, obtaining active metals like sodium from sodium chloride, or even plating, a process called electroplating. In this process, you still need an anode and a cathode. So if you're electroplating, let's kind of investigate that. So electroplating is when you want to take an object and plate it with a metal. So this happens a lot with like silverware or jewelry or something like that. Your anode would be whatever metal you desire to be plated. So if you want to plate something with copper, it would be copper. If you want to plate something with silver, it would be silver. And your cathode would be the object that is to be plated that actually is inert. It's not actually reacting. We're going to plate something on top of it. You would need just one container for this electroplating process, so that means it eliminates the need for a salt bridge that you would have in a voltaic cell because you already can have all the ions that are moving in the one container. You don't have to bridge anything because there's only one container, hence no need for a salt bridge. And in that container, we want to have ions of whatever the coating metal is. So if we're coating with silver, you'd have silver ions. And since this is in a non-spontaneous process, we need a source of electrical energy. So typically some sort of battery, some type of external power source that could provide electricity, could provide the flow of electrons to force this non-spontaneous reaction to happen. We provide the flow of electrons to force it to go, from whatever's oxidized would now be reduced, and whatever's reduced would now be oxidized. You're forcing the electrons to go in a certain direction that normally wouldn't happen. And this is actually called energy coupling if you use a battery, which is something spontaneous, to make something non-spontaneous happen. You would still need wires connecting your anode to your cathode. So your setup would look something like this. So let's say I'm plating a spoon with silver. I'd have this piece of silver, which would be my anode. I'd have this object, which would be my cathode. I connect them through a wire, and I would need a battery. And you can feel free to use like the physics symbol for a battery, which kind of looks like this, or you could actually draw a box and write the word battery in it. And electrons still go from anode to cathode. That's still true in both a voltaic and electrolytic cell. And in here I would have some type of maybe silver solution. How would I get silver solution? Maybe silver nitrate, because nitrate would, is 100% ionizes, and this would be a source of Ag+. And what would happen over time is that the anode's the site of oxidation. So Ag solid, which has an oxidation number of 0, would start turning into Ag+ in solution. Okay, that's being oxidized, and it would lose electrons. And that silver would then migrate over to the spoon and turn back into silver solid. So Ag+ going to silver with this oxidation number of 0 is being reduced, and the spoon would eventually get plated with silver. If this battery were not there, this would not happen. You would just have this container sitting with these two things and nothing would happen. This is a non-spontaneous reaction we're forcing to happen with an electrical source. So let's try to draw a diagram just like this for another situation, and this way we can kind of practice what's going on. So take a moment, try this example, and then check your work. So draw an electrolytic cell for the plating of copper metal onto a spoon. So I would need just one container for this because it's an electrolytic cell. I would need a piece of copper, and that piece of metal would be my anode, because over time this copper would come off of that metal, so it would be going from Cu0, to Cu2+, so this would be oxidized. And I would need my object, so let's just draw a spoon, and this would be my cathode because over time it would get plated with copper. We need a wire connecting anode to cathode, and we need a battery on that wire, some sort of source of electricity, and electrons would go through the wire from anode to cathode. We would need a solution here. Maybe we add copper, copper nitrate of some sort, let's just pick Cu2+. I know I wrote CuNO3, which would be +1 here, but let's say Cu2+, let's pick that. If you have more than one charge for your transition metal, it's okay to just pick one. Cu2+ is typically more common. And we are going to start saying that this is oxidation. So I would be going from Cu solid to Cu2+. And if it's oxidation, I would lose electrons. I would need 2 electrons on the right. And it's actually copper solid that is both the anode and the thing that's oxidized. And over time, the Cu would come off of this metal and turn into solution. And so over time, this would be losing mass. The Cu2+ would then migrate over to the cathode. Since these are mobile ions, they can do so, and that's why we have no need for a salt bridge. And it would start turning into copper solid at the cathode. That's where reduction would happen. Notice I'm going down in oxidation number, and so I would need 2 electrons on the left. And then notice that it's actually the ion Cu2+ that is reduced, and the object is the thing that's the cathode, even though the object is not actually in either of the half reactions. And again, electrons would be going through the wire from anode to cathode. Over time, this cathode would gain mass because copper is being plated onto it. So you can actually determine what mass of, in this case of copper, but in any metal, is going to end up being plated onto your electrode. So how can you do that? This is on your AP Chem formula sheet. You have this equation. I is your current in amps, Q is your charge in coulombs, T is your time. So current, I, has the units of coulombs per second, right? Coulombs per second. And we can see that here on your formula sheet. So if you're given the time and you're given the current through this equation, you can calculate Q, the charge, if you have both I and T. And then we also know, this is on our formula sheet that we've looked at before when we were doing voltaic cells, Faraday's constant tells us how many coulombs per mole of electrons. So if I know charge in coulombs and I know this constant, I can essentially use this as a conversion factor, coulombs per mole, if I have coulombs, and I can end up converting this into moles of electrons. And if I have moles of electrons, and if I kind of go back, I have this balanced half reaction of what's going on. If I know the moles of electrons, I can figure out how many moles of copper is plated, because I see there's this 2-to-1 ratio in this particular reaction. In any reaction, you can just look at the half reaction. So it's this series of steps. If you have the current and the time, you could find the charge. If you have the charge, you can then use Faraday's constant to find moles of electrons. And with the half reaction, you can then find the moles and then mass of the metal that is plated. So this is kind of a flow chart showing that if you have your current and time, you multiply them together, you get your charge. You can then, use Faraday's constant to change into moles of electrons. You can then use your stoichiometry to change into the moles of your substance. In that case, it was copper. And then you could just use your molar mass to change it into grams. So let's look at an example. You might want to pause the video to try it to start with, or feel free to keep watching. A current of 5 amps is applied to a solution of Cu2+ for 30 minutes to produce copper metal. How many grams of copper metal are produced? Okay, so if I go to my formula sheet, remember there is this equation, and just notice that the time is seconds. So notice that I have 30 minutes. It would be helpful to turn that 30 minutes into seconds. And if I do so, then I can use this equation. So you can either use this equation straight up, like plug into it and solve once you get your seconds, or what I tend to do is I tend to use it as a conversion factor. So I noticed that amps, which is the I in this, could also be written as coulombs per second, because amps, the unit amps, must be equivalent to coulombs per second. So again, either way you want to do that is fine. I'm going to show it with a conversion factor, using amps as a conversion factor. But if you don't like that, solve for seconds, plug the seconds in on the bottom, plug the current in here, solve for Q. Okay, and when you do that, I get 9,000 coulombs. Okay, so notice I can track how my units cancel, or if I plug in here, it tells me I'm getting charge in coulombs. Now that I have charge in coulombs, I can use Faraday's constant as a conversion factor. If you wanted to continue this all out in one step, you could feel free to just, get rid of this 9,000 here and tack this on. But notice that the coulombs would go away and I'd get moles of electrons. Now I can go to my half reaction because I have electrons, which are in my half reaction, and I can change that into copper metal. So if I read what's going on, Cu2 plus is being plated to turn into copper metal. Okay, so if I do that, so my half reaction is directly relating copper to my moles of electrons. And again, if you weren't sure how I wrote this, Cu2 plus is turning into copper, and I would need 2 electrons to balance. So we see there's this 2-to-1 ratio. So I'm going to bring that as a conversion factor to change moles of electrons, but on the bottom to moles of copper. And they don't ask me for moles, they ask me for grams. So let's use the molar mass to change moles into grams of copper. Moles will cancel, and you will see that I get 2.96 grams. So again, I'm using the amperage and the time once I change it to seconds with this equation to get coulombs. I'm using Faraday's constant to turn coulombs into moles. I'm using my half reaction to change moles of electrons into copper, and then just massing that out. We can also go the opposite direction. If you have a mass, you can track backwards through the half reaction, through Faraday's constant to change into coulombs. And then if you had, let's say, the coulomb, now that you have coulombs, they give you a certain time, you can find the amperage needed, the current. Let's take a moment and try this example, which is similar, but, kind of going in an opposite direction again. Try it and then check your work. So how many seconds will it take to plate 5 grams of silver from a solution of silver nitrate using a 20 amperage current? Okay, so it might be helpful to write a half reaction for what's going on. In silver nitrate, silver has Ag plus 1 charge. So I'm going, from silver, it's saying plate out from this Ag plus to turn it into silver. I would just need 1 electron. So you'll see everything has a 1-to-1-to-1 ratio. So if I'm using stoichiometry, it's all 1-to-1-to-1. But I can take my 5 grams of silver, and since, our stoichiometry relates moles, let's mole it out. Okay, so I'm moling it out here. And now I'm in moles of silver. I can change it into moles of electrons, the stoichiometry of my half reaction. Now that I have moles of electrons, I can use Faraday's constant, which relates moles of electrons to coulombs charge. And if I do that out, okay, now I have coulombs. And whichever way you're comfortable, if you can either use, this 20 amps as a conversion factor. If I go look at that equation, I see that amps is the same as, coulombs per second, and you can use that as a conversion factor. I would need 20 with the coulombs on the bottom, 1 second on top. Or if you're more comfortable, just get a number here, and you'll be in coulombs. Plug that in for the Q part, which is charge, and then you have your 20, which you could plug in for I, and solve for the T. So whichever way you're more comfortable, you should get 220 seconds. And just be careful. You see there's a Q in a whole other equation for heat. Q is heat. Q is different here. Q is charge. If you kind of remember back to when we talked about, effective nuclear charge and things that affect the force of attraction, we had kind of used Q as charge. We had talked about that then, and this Q is coming back as charge here. We can also do electrolytic cells that don't involve actual electroplating, but we can actually take any redox reaction and force it to happen in reverse. And if we do that, we are creating an electrolytic cell. We would need some type of battery or power supply to make the reaction happen in the reverse direction. So what would normally be oxidized is now reduced, and vice versa. So in electrolytic cells, since a current is applied to the cell, whichever reaction now has the more positive reduction potential. Okay, in a voltaic cell, we said, oh, that thing would be reduced. But now, if we're forcing it to happen in reverse by adding this battery, that thing that has the more positive reduction potential is actually going to be oxidized at the anode instead. And we're going to flip that half reaction. Remember, whichever's oxidized, we got to flip because those are reduction potentials and they show electrons on the left rather than the right. So what's normally reduced will be oxidized instead. And vice versa, whichever reaction has the more negative reduction potential, when we were doing voltaic cells, we said, oh, that would be oxidation at the anode. But instead, whichever has the more negative one will be reduced at the cathode, and we would keep that half reaction the same without flipping it. Okay, anode is still the site of oxidation. Cathode is still the site of reduction. Electrons still go through the wire from anode and cathode. So let's do an example with an electrolytic cell. So if you want to, go ahead and try this example by yourself and pause the video, or you can just watch me go through the example. So complete the diagram for the electrolysis. Electrolysis implies electrolytic cell of NaCl liquid. Fill in any missing parts. Notice it's one container because it's an electrolytic cell. I have my two electrodes. One says anode, one cathode. I have a wire. The wire's not connected. I don't want to just connect the wire. What else do I need? If it's an electrolytic cell, I need some type of battery. I need some type of external power source. And however you want to show a battery, if you want to show like that physics symbol for it you saw before, if you want to just write the word battery in a box, cool. Okay, I don't need a salt bridge. I only need a salt bridge for voltaic cells. Since everything's happening in one container, I'll have mobile electrons that can flow in the container. I'm cool without a salt bridge. There's nothing to bridge. Okay, it says write the half reactions taking place at the anode and cathode. And you'll notice here given, instead of giving you a whole chart, I just give you what you need, which you would usually see in an AP problem. So here's the two reduction potentials. As I had said in a previous video, the one with the higher reduction potential doesn't have to be on top. So just notice, here it happens to be, but it doesn't have to. They don't have to put it in order for you. So if I look at this, I always like to think about, okay, what would happen if this were voltaic? And then I'm just going to switch it. So if this were, and also, it would be helpful Notice I also need ions in here, even though I don't need the salt bridge. I do need ions in there, in this case Na plus and Cl minus, because that's what's happening in here. And we'll talk about the half reactions going on and how they're produced or used. Okay, so if voltaic, whatever had the higher reduction potential would get reduced, and that would be at the cathode, and whatever had the lower reduction potential would get oxidized. However, since this is electrolytic, I am going to flip this. The one with the higher reduction potential, I'm going to force to get oxidized. I'm going to force this in reverse. Okay, so since it's electrolytic, this would happen at the anode, and since it's oxidation, I'd have to flip it. And this half reaction would happen at the cathode. Okay, so at the anode, this one. At the cathode, but flipped. Cathode, this one. Okay, so I'm going to label that here. So since this is the anode, I want to make sure electrons are there on the right. I'm going to flip it. And here's my half reaction at the cathode. And how do you know this is a liquid? Just because it's talking about liquid there. That's why I put it there. Okay, so write the balanced reaction. So to get the balance, I got to add the two half reactions together. And notice I put 2's in front here because I got to make sure the electrons are equal. If you wanted to write a half reaction without the 2's, that's not going to change the reduction potential, remember? So it's totally up to you if they just asked for the half reaction. But if they ask for the overall, don't forget to multiply by 2. You add them together, and I get your choice of writing either Na plus, 2Na plus 2Cl minus, or you can combine it together and make NaCl, NaCl liquid, since that's what it's telling you. Okay. Determine the voltage required for the electrolysis. So E of the cell, remember, it's still the same way as we did for the voltaic. It's either cathode minus anode, or you can take the anode one and flip the sign, and add them together. Either way, you should get the same answer. I like doing cathode minus anode and not worrying about flipping things. You would still have to flip the half reaction, don't forget. So, on this side. So cathode, here we go. Cathode is negative 2.7 minus the anode 1, and you will notice that you get a negative voltage. You should always get a negative voltage for electrolytic. Why? Because we are forcing this to happen in the opposite direction. Okay, it is requiring this input of voltage. So if I need voltage required, I would have to put in 4.07 volts or more. This battery would have to be rated higher than 4.07 volts. So if I had like a 1.5 volt battery, it would not do the job, and this reaction would not be happening because it's non-spontaneous. Indicate the flow of electrons and flow of ions. So electrons still go through the wire from anode to cathode. That is true in electrolytic. It's true in voltaic. Flow of ions. So let's see what's happening. This is my NaCl liquid. That's what it's telling me here, which, the ionic liquids, are consistent of your ions in, mobile ions. So this Na plus can travel over here and turn into Na liquid at this cathode, and the Cl minus would migrate over to the anode and turn into Cl2 gas. So you might see like some bubbling over there. And notice you still have this flow of ions, and if you're thinking about a circuit, your negative electrons are going this way, your negative ion is coming back this way. So you still are completing the circuit without actually needing a salt bridge. Explain why NaCl solid cannot replace NaCl liquid. Why do I need a liquid and not a solid? Because you still need these ions to be mobile in order to travel over to the electrode, because it's at the electrode that the oxidation and reduction happen. That's where it's losing the electron, that's where it's gaining the electron. Ionic solid, if this were a solid in here instead of a liquid, the solid would have the ions locked into a lattice. They would not be able to travel to the electrodes, and no reaction would be able to happen. So remember that this needs to be a source of mobile electrons. Ionic liquids are a source of mobile electrons, as well as ionic solutions. So that's a little bit about electrolysis and electroplating. So again, just to kind of recap, anode and cathode, the higher reduction potential we normally said would be the cathode, and the reduction half reaction happening in a voltaic cell. Now we are flipping that. The higher reduction potential is the anode, because we're forcing it to go in reverse. The things that don't change, it's still getting the E of the cell is still cathode minus anode. The anode is still the site of oxidation. The cathode is still the site of reduction. Electrons still go through the wire from anode to cathode. Your negative ions are still going in the opposite direction to complete the charge. But you do need a battery. You do need one container. So whenever I'm doing electrolytic, I always, for some reason, for me, voltaic makes more sense to think of it first, and then I flip what's the anode and cathode.